Hello, this is Advent of Code 2024. I'm Noah Mann. I'm the author of FunctionalJ.io, which is a Java library that brings functional goodies to Java. Today's puzzle is day 11. All the code discussed in this video and the link to what mentioned above will be in the video description. Let's get started. Today's puzzle is called Plutonian Pebble, which is about very strange stones. Each of the stone is engraved with a number. The strange thing about this stone is that every time we blink, it changes in some way. Some of the stone change the number that is engraved on it. Some of the stone split into two. If the stone is engraved with 0, when we blink, it will change to 1. If the stone is engraved with a number that have even digits, when we blink, it will split into two stones. The first one have the left half of the digits, and the second one will have the right half. And if the stone is not fit any of these rules, it will change to another number, which is the multiplication of the original number and 2024. Let's take a look at an example. This example start with 125 and 17. 125, because it's not 0 and it doesn't have even number of digits, so it changed to 125 times 2024, which is 253,000. For 17, which is 2-digit number, so it's split into two halves, which is 1 and 17. In the next round, 253,000, because it have 6 digits, which is even number, so it's split into 253 and 000, which collapse to just 0. Then 1 is an odd number and it's not 0, so it changed to 2024 times itself, which is 1. And then 7, also the same, so it's 7 times 2024, which is 14,168. If we continue the next round, 253 is odd number, so we times 2024. 0 turn to 1. 2024 split into 20 and 24. 14,168 times 2024, we got that. And this continue round and round and round. The question asks, how many stones we're going to get after 25 blink? Part 2 is the same, but with more iteration. Part 2 asks 75 times. During the competition, I just do a naive solution, which is a recursive. Just recur from one to another, and it takes not so long for 25, but almost never finish for 75. Definitely, there have to be some sort of optimization. So how would we solve this? First of all, we need to recognize that because sometimes the stone split into two, so this problem expands exponentially. It might not do for every number, and might not do for every round, but at some point it's split into two. And sometimes there are more stones in the same line that split into two. So this is definitely exponential problem. Another observation is that the growth of the stone are independent. So for 125, it grows by itself. It never cares that it sits next to 17. The same goes to this number. It never cares that next to it is 1. And every of them will grow by its own. With this in mind, we can solve this problem using graph technique. Because if you look at it, you see that if this is a node, this is a vertex, this is a node, and point to those two nodes and point to other nodes. So these are sort of graph, or you may call it a tree, same way. And we can solve this using that first search. So basically we go here, go there, go there, go there. Once we get to 75, we just come back. So let's say we only care about 4, for example. So we go here, 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 and then we come back to this, come back to that. We know that this split into 2, so we go down this route instead. And to solve this, we can use recursion. But because it's grown exponentially, so we will go on and recurse over this over and over again. It's too slow. So we need to find a way to optimize this. First thing we can think of, I'll say this quickly, it doesn't help much. But if we remember that for 25, one step after it will have 1. We can remember this. and after that is split into 2. We can remember that 253 after 2 step. So this is at 1 step. So this is at 2 step. 2 step is 2. And at 3 step, it's split into 3. Right? If you take a look at it this way, you can catch that for this number and for the number of times that we got, how many loops are there. But let me tell you that this is not much of a help, at least for the implementation that I did, because if we want to know more, we have to start from the beginning. So I come up with a different technique. And since the naive recursion doesn't work, and the naive dynamic programming turned out to be not much helping, at least for my implementation, I come up with another technique from the observation that there will be a series of one stone chained to another stone, like this one, chained to this one, and then split into 2. Same here, this one to 1, and split into 2. This one, split into 2. This one to this one, and then split into 2. Right, so 1, 20, 24, and split to 20 and 24. Later on, if we found another one somewhere, let's say we found another one here, we know right away that the next step will be 20, 24, and after that will be 20 and 24. And if we want to know further down, we can go to 2024, and if we already calculate for 2024, we will know that the next step will be 1 stone at 40, 48, and then it's split into 40 and 48. So from this, it should help speed things up. We just go from one chain to another change. Let's see some example. Apologize first, that is flipped from before because we put 2 ends on the top. These are 7 blink change that I arranged it so that easy to see. Starting from 0, it go to 1 and 20, 24 and 20 and 24. Then 20 go there, 24 go there, and 2 go to that chain, 0 go to that chain, which is a copy of this, 2 go to that chain, and 4 go to that change. So let's say if we already have this in the cache, and we want to know how many stones from 0 in 1 step. For this change, it's 3 singles, and 0 is at the index number 2. For 1 step, from index 2, we subtract by 1 is still greater than 0. So that means that it's still in the single list here. If it's still in the single list, you know that the number of stone is 1. So if the steps are within this range, the number of the stone will always be 1. So if the number of steps is exactly equal to the range, the length of the singles plus 1, in this case it's 3, so 1, 2, 3, then we know that the number of stone is 2. Otherwise, if you want to know greater than the number of singles here, let's say 4, so we know that we need to get the number of steps from the chain 20 go up 1, right? So from this number, we know that 20 split into 2. So the answer is 2 on this side and 2 on this side. So the number of stone at this step, which is what? 1, 2, 3, and 4. So at the step 4, the number is 2 plus 2 equal 4. So just to complete, at the step number 3, 1, 2, 3, the number is 2. At step 2 is 1. At the step 1 is 1. Then if you want to know step 5, you can ask on this side first, you can ask chain of number 20 for 2 because it go beyond this, it have to ask 2 for 1 more step, which return 1 here, and ask 0 for 1 step, which return 1 here. So plus together you get 2. So 2 on that side. So 2 on this side in total, and 2 on this side in total. So at step 5, you get 2 plus 2. So 2 come here, plus 2 come here, you get equal to 4. Then at the 6, we split this into 2. So this side is 2, this also split, and this also split. So at the step 6, we get 2 plus 2 on one side and 2 plus 2 on another side, which is 8. So this way, we can reuse the change that we already have. So with this method, I'm able to implement an algorithm that runs within milliseconds. Let's take a look at the code. So here's the code of the blink change. So the blink chain is composed with 2 ends and a list of singles. I use long because the number can grow quite large. So we can add a number into the change and return the index to it. We can create a blink. So a blink is just a reference to a change and the index to a number. So this way, the change 0 can be linked to chain 1, can be linked to chain 20, 24, and end up with 20 and 24. This can be one blink. So this will be blink for 24. And this one is blink for number 1. And this larger one will be blink of number 0. Let's see how blink look like. Blink is a record of blink change and the index to the change. So in the previous example, we have 0, 1, 20, 24, and 20 and 24. So this is the index. This will point to index number 0, and this is index number 1. This is index number 2. So the blink of number 0, blink of 0 is point to index 2 of this change. So this way the chain can be reused. You can see from here, when we want to get a chain of a number, we just see that if it's already there or not, right? If it's already there, we just return it. Otherwise, see if the number is 0. If the number is 0, we just get the blink of number 1 and then chain it with 0. By chaining, you can see it just add number 0 in this case into the chain. So it's just array list that extend one things here, and then we create a blink to wrap around it. And we check if the digits count is even. If so, we just split the number into n1 and n2. Then we create a new blink change and then add the number as a chain. So let's say you put 20, 24. We split to 20 and 24. So that 20, 24 and add 20, 24 here. And lastly, if it not fitting this two, we just time it with 2024. This is exactly like what the question asks. Now let's see the component that use it. In this case, I called it stone counter. Stone counter has a cache for each known count, which is the cache for number and times. So if we have seen that number and that many times before, then we can use this cache. And then we can ask for the count for the number of time. Of course, to look in the cache first. Otherwise, it just try to calculate it itself. And to do that, it just get the blink of the number and then see the index. If the number of times that we want is less than the index, we just return 1, right? It's it within the chain. Again, I will use the same chain so that you can see. Index is number 2, right? So if you want 1 or 2, it will be within this singles. So we just return 1. And if it just exactly one more from the index number here, we just return 2. Otherwise, we just get a change of this guy, get the change of this one, and then ask it for whatever we have left, then sum them together. Then to solve the problem, we just get the lines and then extract the first line of the problem and then found the number. We parse it to long and then ask the stone counter for each of those numbers and then sum them together. That is it. We get the solution. So for 25 round, for 25 round, the production input get that number. So if we take a look at part 2, that is 75 round. That is a number of the stone that we have. That is it for this video. Before you go, Before you go, all the code discussed in this video can be found in my GitHub. The link will be in the description. You can also find the link to functionalj.io, which is easy to use with these Gradles and this Maven. Please give it a try. If you like this video or learn something from this video, please click like. If you want others to learn as well, please share. If you have question or disagree with this solution, or you want to show off yours, please put your comment in the comment section. And if you want to see more, please subscribe. Thank you very much for watching. See you again in the next video. Bye bye.